Okay, so before I start on something new, is there any question regarding the lab session or lab type session that you had? So you see that was the first model that he presented, although this was much general because it's not very normal, but the results were all wrong, meaning economically they are not meaningful. So you cannot present a model like that because the first requirement is that the coefficients have to be all non-negative. Okay. So if you are running several models, among other things, you need to check those. Those are much more important than statistical significance. You cannot say that well, land has negative coefficient. It's not justified. Okay, whether it's significant or not, that's kind of a different issue. Okay. I might, again, depending on the situation, I might show some of the codes using SFA. Okay, so since we talk about both input and output oriented model, and the focus so far was mostly on output oriented model. So the input oriented model, remember the main objective, I mean if you remember the graph, we are going westward. And we are thinking in terms of using less resources if possible. When we go to the frontier, we are thinking in terms of reducing the use of X. Okay? And X can be any of the inputs. So in one application, we used Indian banking. So we were thinking that whether banks are using labor optimally or they are overusing labor. Right? They are employing too many people in the bank. So what we did is we were talking about again like input-oriented measures because we are thinking in terms of possible reduction in labor without reducing output that banks are producing. So what happened is that when you are thinking in terms of input-oriented measures, it matches with what we call cost minimization. Because what you are doing is you are thinking of reducing your inputs given the output, and that is consistent with what we call cost minimization. If you remember the micro theory, okay, or again micro class, then we talk about cost minimization as again I will show you some graph that the objective of the form might be to minimize the use of resources to produce a given level of output. Okay, and that happens not to everything, but mostly for the service industry. Because in service industry, if you think in terms of supply of electricity or water, okay, I mean they cannot produce as much as they want, right? Because what is the point of producing electricity when there is no demand, right? So this is what we call demand determined industries. And the service industries are like that. Okay, so let's say when you go to a hospital, the doctors are there, nurses are there, but there is no patients, right? So your objective should be that the number of patients is outside your control. The hospital cannot control. They cannot force you to go to the hospital and get treated, right? So there are cases, this type of cases where output is exogenously determined. It's not in the control of the farm. But if you are making shoes or shirts or again producing other things, then it's your decision. If you are producing more than what is sold in the market, you can keep it for the next year, right? So again, so there are two types of situation. One where we are talking about service type industries, where outputs are exogenously determined, and then the other one is the regular case where output is going to be determined by the firm, again by maximizing profit or that type of thing. Right? So here again, I'm going to be talking about cost minimization. That means output is going to be exogenously given. So think in terms of again like a production function. I'll go through a little bit of algebra, but again this is not econometrics. Again, I'm assuming, as I mentioned before, that math is not a problem for you or should not be a problem for you. If you say it's a problem, I won't buy that. I will say, no, you are not telling me the truth. Okay? So again, the production function, I'm just writing y equal to f of x and z. So z, again, you can include if you want to, or you can say that, well, f is a function of x only. So the way we distinguish often between x and z is that x is regular inputs and z is what we call sometimes facilitating inputs. Right? That means it's not directly inputs like capital lever and land and that type of thing, but it's kind of the environment. Right? So I think in terms of rainfall or temperature and that type of thing, they are not directly used in the production, but indirectly they help. If there is too much rainfall or there is not much rain, or if you have things like that, there is no sun, then again like your output is going to be affected. But it's not like you can buy more sunshine or buy better weather, right? Which is the case for regular input. So this is how we often distinguish between an x and z variable. Okay. So again, the point is that you have a technology which is given by this, and then your objective is to minimize cost. Okay. Because remember, I'm just thinking in terms of service type industries. So you're minimizing cost, input cost, subject to the production function. So this is a constraint. And you know that when you are minimizing or maximizing a function with constraint, you have to define a Lagrangian, right? So you all know that. So this L is the Lagrangian, which I write W prime x. You have more than one x, and then plus lambda Lagrangian multiplier, and then y minus f of x. Okay. So this is the function that you are minimizing, and f of c is the first order condition with respect to each of the x's, right? So jth x, you take a derivative of this with respect to xj, you get wj. And then from here, you get, again, like x is in here, so take a derivative of that. With respect to x, you have lambda in front and your minus sign, so minus lambda and del f del xj. Okay. So that first order condition, it has to be equal to 0. Okay. So I forgot to put that here. So that's kind of the first order condition. Again, what it means is that you can figure it out what is happening in here. That means the value of the marginal product is going to be equal to the prices of the inputs. Now, since you have lambda, and lambda is something that we are not interested in, you can think of lambda as the nuisance parameter, right? You need to have that set up, but again, like we're not getting into it. There is no apparent meaning to it. So we need to get rid of that. How do we get rid of that? Well, take a ratio of this thing. So Wj over W1. So think of 1 as the first input as the numerator. Then you can do something like this. Wj over W1 is equal to lambda gets cancelled, Fj over F1. And again, what is this Fj over F1? Economically, this is what we call marginal rate of technical substitution between input j and 1. And this is the ratio of input prices. So again, in terms of graph, again, this is kind of standard micro. I mean, first year, micro class, we learned this thing. That means you have two inputs, x2 and x1, and this is the ISO point. Okay. So the production function, instead of production function, we said, well, if you set y at a particular level, then it's a function of only x, and then you have two x's, x2 and x1. So you can have the ISO point, which is associated with a particular level of output, right? If output goes up, then again your ISO point will move, okay? And then again, you just look at the first order condition. So what is happening is the ratio of input prices is ratio of the marginal product, and that is given by the point of tangency. So the point of tangency, this slope is, in terms of this, the ratio of the marginal product, and then again from the cost function you get the ratio of input prices. So this equality has to hold, and this is given by the point of tangency between the ISO point and the ISO cost line. So this is called ISO cost line. That means every point on this gives you exactly the same cost. Okay. So the question is that if you want to produce this much, what is the best way of producing? That's kind of given by the point of tangency. If you go to another point, something like this, you are producing the same level of output. But remember, that then line has to move, which means your cost is way higher. So that's not the optimal point. Optimal point is given by the point of tangency. So this is the graphical representation of this condition. Okay. So now going back to the math. So again, this is a ratio of two things. So J is running from 2 to big J because you are using 1 as the numerator. So how many equations are there? How many? So big J is the total number and little j is running from 2 to big J. So how many? J minus 1, right? So you have J minus 1 equations and the production function is another equation. So you have J equation to solve for J unknowns, which are the inputs. So you need to solve for the inputs. What is the optimal quantities of input? This is for x1, this is for x2. How do you figure it out mathematically? Well, you solve this equation. You have, if J is equal to 2, which is what is shown in the graph, then you have 1 in here because J is running from 2 to big J, which is 1, right? So one equation in here and one equation is given by the production function. So you solve those two equations to get your x1 and x2. These are going to be optimal quantities of x1 and x2. So this one you can just say x1 star and this is x2 star. Okay. So these are optimal quantities of x1 and x2 that will give you the lowest possible cost to produce the level of output which is given by this y here. Okay. So again, without getting into this two input case, in general we can say that well, you have J minus 1 equations and this one is 1, so J equation for J x's, and implicitly you can say that well, the solution of those x's will be function of what? Function of everything else. What are everything else? If you look at it, everything else other than x is what? Y and in prices, right? So this is going to be a function of y and vector of input prices. Okay. So again, we call these things as conditional input demand function. Demand for each input is a function of how much output is being produced and prices of the other inputs. And I put the subscript j to indicate that well, you can figure out the demand function for each input. Okay. Now you can plot that optimal quantities and in the definition of cost. What is the definition of cost? Cost is sum of this cost of each input. So Wj times Xj. So this Xj is coming from here. Okay, it's a function of y and w. So the cost is going to be a function of y and w. So again, when you look at any textbook, okay, no matter what level you are looking at, you will see that well, cost is specified as a function of output and input prices. Now, most of the time we just say, well, in a perfectly competitive market, input prices are exactly the same for every firm. If you believe in that, then again, this is a constant, so cost is a function of output. And that's what you see in a textbook. So you will see a graph like this. This is cost on this side and output on that side, and this is an increasing function of output, right? Because what is the rationale? Again, this is the marginal cost. That means if you want to produce more output, can you produce with the lower cost? Can you produce more with the lower cost? No, it's not possible, right? So if you want to produce more milk, then you have to increase your cost, right? And the cost is increased because you have to have more cattle or more of other things, right? So right now we're not getting into that. We are just saying that we solve for optimal quantities of those. So again, cost is a function of this output level and input prices. If input prices goes up, given everything else, your cost is going to be increasing. So the derivative of cost with respect to input prices will also be positive. Okay. So again, so this is coming from economics, or maybe that you can say that well, economics in here is the basic intuition. Again, you don't have to be a PhD to understand the implication of it. It's as simple as that. If in order to produce more, you have to pay, your cost has to go up, right? There is no way by which cost is going to be lower when you produce more. Okay. Okay, any questions? Okay. So then there is something else, which you may not have, what's called Schaeffer's lemma, meaning that well, if you take a derivative of the cost function with respect to input prices, you get your excess. That means input demand can be simply obtained by taking a derivative of the cost function with respect to input prices. And that is obvious if you follow the mathematics in here. That means if you take a derivative of this with respect to input prices, you get your x, because this is going to be equal to 0, the optimal, with y equal to f of x. So this part is equal to 0. Right? So there are many different ways of looking at it. You can look at it purely from a mathematical point of view, or you can think of the mathematics combined with economic intuitions. Okay. So again, this name Schaeffer's lemma is used, but again, if you don't use the name, you can simply say the derivative of cost with respect to input prices is going to be giving you the input demand. Therefore, if you take a log derivative, instead of looking at the derivative, if you take a log derivative, then this is going to be what? Log derivative is going to be like this is going to be what 1 over c del c del wj, and then multiplied by wj. So you will be getting wj xj divided by c. And this is the regular derivative, this is the log derivative. Okay. And what is this? This is the cost share. So sometimes what we do is we specify the cost function in log terms, just like the production function. Remember we did a Cobb-Douglas production function, we can do a Cobb-Douglas cost function also. So that's going to be in log, so we'll be dealing with log derivative instead of regular derivative. Okay? And again, when you take a log derivative, that is going to be giving you the cost share. Okay? So this is kind of a backup, just to refresh your memory in terms of what goes on in a standard textbook, okay, about the cost function. Now we have not talked about inefficiency yet, so what I'm going to be doing is now bringing inefficiency into the picture. Right? So again, as I said, well, I could have gone straight in here, but I thought that let me briefly get to the rationale behind the cost function and then introduce this inefficiency. So now again, it will be repetition of what I did. Okay. So what is the production function with inefficiency? Remember, this is input oriented inefficiency. So you are using x, but that's what less than, you are using 10 people, but it's what less than 10, it's maybe 8, so you have to adjust it for your inefficiency. So this is input oriented inefficiency. E to the power minus eta is less than 1. So this is kind of the factor that is scaling it down, and we are assuming that to be proportional to all the inputs. So x is a vector, but again this is a scalar. That means you have, you can think in terms of scaling it down by the same proportion. Okay, so now again write down the first order condition. So what is the difference between this and the one that I showed you? Okay, so this was y equal to f of x, and this time you have y equal to f of x times this. So in your mind, this is what I always tell people, that if you have difficulty in following the math, keep a picture of the previous one in your mind, and you say what is the difference between what you saw before and now. The difference is that, well, x before is replaced by x times e to the power minus eta, right? So in your mind you just say that, well, whenever you saw x before, you just think in terms of x times e to the power minus eta. So this is kind of input adjusted for inefficiency. You need to say something? Okay.
This meeting is being recorded.
Okay, so if you write down the first order condition, it's going to be exactly the same. The arguments is not going to be x, but x times e to the power eta. As I said, well, you keep your that type of changes in your mind, and the right hand side is going to be the ratio of input prices. So the point is that, well, if you replace x before by x times e to the power minus eta, then these two things are exactly the same, right? You don't have to do any extra math, because you said, well, I have already done it, and then you just said, well, replace x by x times e to the power eta, and then you'll be getting your cost function for inefficiency. So then again, the cost function with inefficiency is going to be defined in this way, okay? So this is again w times x times e to the power minus eta, because this is the cost of inputs adjusted for inefficiency. So you are not talking about 10 people, but you are talking about 8 people, right? So this is again a construct. This is not actual cost. Actual cost is going to be wj times xj, and this is the minimum cost, right? The minimum cost is obtained by multiplying this efficiency adjusted inputs by their respective price. So this is not what you see in the data. Okay, so what do you see? That means you have to relate this to actual cost, because this is not something observed. And what is actual cost? Actual cost is cost of input. So what is CA? So this is equal to summation of wj xj. So we have to show the link between, sorry about the handwriting in here. So what you have to do is, we have to show how actual cost is related to the optimal cost. Now again, like there are a few lines of math, but think in terms of this. Because of inefficiency, every input is increased by 10%, for example. So can you tell me by how much cost is going to be increased? Every input is used by 10% more. So by how much cost is going to be increased? 10%, right? So as simple as that. So again, here I have few lines of math, but in the end, what you get is like this. Okay. So in the end, you get actual cost is minimum cost plus eta, because eta is telling you by how much the inputs are increased, and therefore cost is going to be increased by the same proportion. So log of actual cost is log of the minimum cost plus this input oriented inefficiency. Right? And then I added V in here because again we need to add a noise term to estimate the model econometrically. Okay. So then again, like you can define cost efficiency in this way. That means your minimum cost divided by actual cost, so that the number is again between 0 and 1. Okay. So again, this is the minimum cost. Your actual cost can never be less than the minimum cost. It's going to be always bigger or at most equal to. So this ratio is going to be again between 0 and 1. So this is consistent with technical efficiency or output oriented efficiency. Okay. Alternatively, you can just say that, well, what is the meaning of that? So if you take this minus 1, so that is approximately equal to eta. That means it's just showing that there is a percentage increase in cost because of inefficiency. And again, I give you the intuition that if every input is increased by a certain percentage because of inefficiency, cost is going to be increased by exactly the same percentage. So this is what is happening. Okay, after doing all the math, it's just, well, this is obvious, right? And that's what it is. Okay. Okay. So now the question is, okay, how do you specify this econometrically? Because you have to estimate it. We are interested in estimating the parameters associated with the cost function, the minimum cost function, and we are also interested in estimating cost inefficiency. That means the percentage increase in cost because of inefficiency. So what you do is, again, here I have a task log specification, but never mind with that. So this is the minimum cost, and we are specifying a function for that. So let me just do something like this. Okay, if I cross out this part, so let's just get rid of this. Then again, what is it? This is a Cobb-Douglas cost function. What is Cobb-Douglas? Cobb-Douglas is a log linear function of the arguments. Right? In a production function, arguments are inputs. So when you take a log linear, then log of y is equal to, again, a linear function of log of x's. Right? So here again it's a log linear, and the arguments for the cost function are w and y. So you take a linear function of this with a log of y and log of W. You have a single output Y, so this is the coefficient, and these are the coefficients of the input variables. Okay. Now there is a couple of things for a cost function. Okay, well, you don't need this thing. I mean, because I cross out the other terms. So what happens is there are cost function, we just say that the homogeneous of degree 1. So again, what is the meaning of homogeneous of degree 1? Again, you may have seen a function is defined as homogeneous of degree 1 if you increase the right hand side by lambda, the left hand side will increase by lambda. Okay. Now, why cost function is homogeneous of degree 1? Okay. So what is the definition of cost? So the definition of cost is, what did I write? Okay. So this. So if the prices go up by lambda, what will happen to cost?
Increase by lambda.
Increase by lambda. So this is not an assumption. This is kind of a definition of cost, right? So do not try to say that, well, this is kind of, I'm imposing a restriction for the cost function to be homogeneous of degree 1. It has to be satisfied, okay? Because it's coming from the definition of cost, okay? So again, if it is homogeneous of degree 1, then again there will be some constraint imposed on that, and that is basically sum of the beta j's is going to be equal to 1. That's kind of if you restrict this, then it will be automatically the function is going to be homogeneous of degree 1. So one easy way of doing it is divide your cost by one of the input prices, and on the right hand side your input prices are going to be also divided by the same one. So that way you don't have to worry about imposing it separately. You normalize your cost, okay, with respect to one input price, and also the other input prices again normalized by that. Which one doesn't matter, okay? So if you have 5 inputs, use any one of those, price of any one of those, and normalize both the cost and other input prices. So that price is not appearing directly, okay? So this is a function of, see that while I put tilde in there, and tilde is defined as the ratio of that. So W1 is out of the picture, okay? Now since W1 is out of the picture, you are not able to get beta 1, right? But what is, if sum of the beta is equal to 1, then what is beta 1? It's 1 minus sum of the other betas, right? So you are not losing anything. You are able to recover all the parameters, okay? Even though you just write it out like this. Okay. So in the end, what happens is, let me just write that down by creating a page in here. So what is happening is, if it is a Cobb-Douglas cost function, so you are writing it out like this: log of actual cost, okay, is a linear function. So let me just write beta 0 plus beta y log of y. Okay, and again this is normalized, so let me just do it like this so that you don't get confused. And then again like beta j, okay, sum of beta j, j is equal to 2, not from 1 to big J, and then log of wj over w. Now even if you put j equal to 1, what will happen? W1 divided by W1, which is 1, right? What is log of 1? Log of 1 is 0, right? So again, if you fail to put that in, it's automatically going to be equal to 0. But, okay, and then again you are going to get eta, and then plus V. So again, V is noise, which is ad hoc, and again this is input-oriented inefficiency. So now if I ask you, do you see any similarity between the production function and the cost function? Or dissimilarity? Mathematically speaking, what is the difference between a production function? Let me write it like this. Production function is like this. Okay, so let me just write it in a different notation. Okay, alpha j log of xj plus V minus U. So I'm just putting them side by side. Now again, don't try and argue that, well, this is Y and this has X. No, you just think in terms of mathematics, these are notations. So forget about whether it's X or Y or W. Now think in terms of, again, a variable. So when you look at these two side by side, okay, what is the difference that you see? On the right hand side, you have some variables. In here, you have also some variables. Right? The variables are different, but again, as I said, well, that is not the point. Okay. So then again, what is the difference? You have V, right? What is happening? Here you have theta and here you have minus it. So this is positive and this is also positive. So what is happening? You have plus sign in here and you have minus sign. Okay? So that is the only difference. So remember, he was saying that, well, orientation, okay? And then you have to put O in there, output oriented. Now if you want to estimate a cost function, then you have to change the orientation, okay? Now this is the package. He was using SF cross. Now if you don't use SF cross, but again like some other command to estimate it, one is by default, output oriented is by default. If you want input oriented, then you have to say that is a cost function. So they specify it as a cost function versus production function. For a production function is negative, for a cost function is positive. Right? So do you need a separate program? No. I mean, it's exactly the same, right? The only difference is the sign. But if you think in terms of pure mathematics, mathematical point of view, you say, or blindly follow this, then how do I get from here to there? Well, multiply everything by minus 1. So then again, like, V will be minus V and U will be plus U, right? And V is symmetric. So plus V or minus V doesn't matter, right? If something is symmetric, the sign in front of it is symmetric. Right? So another way of saying is that, well, if you have only one program, right, that means output oriented measure, you can still estimate a cost function. All you have to do is every variable has to be multiplied by minus 1. Okay? And then when you get the parameters, you have to also multiply by minus 1 just to see that, well, because you multiplied the variables by minus 1. But again, you don't have to do it. But I'm just saying that, mechanically speaking, one program is enough, right? But I mean, it is still one in a way that you have to specify the orientation. Okay. So again, as I said, you don't need to know anything new. There is nothing new in a cost function estimation. You go to the same program, and then again, if you are using SF cross, then you have changed the orientation from output to inputs, right? Okay. So, but again, like in terms of data, to estimate input-oriented inefficiency, the data is completely different, right? In a production function, you are using data on output quantity and input quantities. Now, these data are readily available for most of the cases, right? Now, when you estimate a cost function, remember, you have to get data on cost. Now, that is not probably that difficult because this is the total cost of variable inputs, yeah? And then again, this output, which is probably not difficult to get. The difficulty is in here, getting input prices. Now, most of the cases, you don't get input prices, or even if there are, you get the information on input prices, there may not be much variation. Okay, so if you are looking at price of fertilizer, and I ask all the farmers in Haryana that, well, what is the price of fertilizer that you use? Think of a particular type of fertilizer. Probably everybody will be saying that price is exactly the same. There might be a little variation here and there, depending on where you bought it, whether you bought it in this town or the next town or somewhere where you can get a better deal. But again, these are very minor variation. And in econometric estimation, what happens is that you have to have variation on the independent variables. If there is no variation or very little variation in the independent variable, your estimates are not going to be good. What do we mean by that? That means you won't be able to, you can draw a line. So if I give you points like this, okay, so if I give you a bunch of points like this, and say that, well, I will fit a line, you will be fitting a line, but you are not going to be very comfortable with that, because again, if I add one data point, you might be saying that, okay, the line shifts. Okay. But if there are points like this everywhere, then again, you have much better confidence in saying that, okay, the fit is robust. It's not going to be changed if I take out one point. So again, the variation in independent variable is essential for a good estimation of econometric model. So the cost function has this problem if you don't see enough variation in prices. Now, again, if you come to think about it, that why should there be variation in input prices if you think that market is competitive? So it's kind of contradictory. Sometimes we just say that, well, okay, price of the input should not be varying much. Okay, it depends on how you measure it. Sometimes we use labor as the number of heads, number of people. But if you look at the university, for example, in here, and then look at how many people are working, and that includes the vice chancellor as well as the people who are cleaning the floors, right? So then again, if you ask that how many employees are in there, they will say that, well, there are 5,000 people working. So you get the 5,000 number. But again, now if you think in terms of quality, is there any quality difference? Of course, the sweeper, I don't know how much he gets, and then again, I have no idea how much the vice chancellor gets, right? So there will be a factor of maybe 100 or 1,000, I don't know, of the salary of vice chancellor. But again, so looking at the number of people working, that's a very bad, so what happens is that instead of looking at number of people working, you might be looking at the cost of labor. Because the vice chancellor, if he gets 1,000 more than a sweeper, then again, like vice chancellor is 1, and then again you get multiplied by 10,000 to make it comparable to the sweeper, or divided by 10,000. So this is going to be adjusted for. So very few times we do it because we don't know the salaries. For example, I don't know the salary of the vice chancellor. I don't know the salary of the sweeper. But again, I have information about the number of people. So they just use number of people. The same thing for banks. So we did a study, I told you that was on Indian banks. But the good thing is that at least in India, for banks, we have the data is reported like class 1, class 2, class 3, class 4, right? So again, I don't know which way it goes. Class 4 employees are the sweepers or clerk and that type of people. So we have, for each bank, we have data on how many people are in each category. So then when we are good that one, we can control for quality of the inputs by looking at those type of classifications. But let's say you go to US and banking data there is freely available. You can go to Chicago Fed and download the banking data from there. Okay, it's free, but again, they don't have this type of information. Of course, in US, they don't have this class 1, class 2, class 3, class 4, but they also have it because everybody is not getting the same salary. The people who are working as a tailor, they get a lot less than the manager, okay, or the CEO, for example, meaning the president of the bank. So this quality variation is there, and again, they report number of people working in each bank. They also report the cost. But unfortunately, most of the people use the quantity data and they don't control for the quality. Okay. But again, you know that should be the case because it does not make much of a difference to equate vice chancellor with the sweeper. Right? Okay. But again, if you have the data on the and that's available because if you know how many people are working, they will be also reporting what is the labor cost, what is the cost of material, what is the cost of those things. So you can replace your X, again in the production function, replace X by, instead of the physical quantities, you can just look at the values or the cost of those things. So I think that's a kind of a better measure than looking at simply the number of people working. Okay. So anyway, so this is the point I wanted to make. So that means you don't need to do anything extra in terms of estimation. You just change the sign from minus to plus, and that's going to be interpreted as, you know, the input-oriented inefficiency. And then again, the interpretation of that is the percentage increase in cost because of the fact that you are not allocating your inputs efficiently. Okay. Now again, like given when I will finish in 5 minutes. So what is happening is, now let's just show you another picture. When I did the first order condition, I was looking at the, so I think these are distributed to you. Okay, so again, like in the last session, he was talking about allocative inefficiency, which we have not mentioned. So we are focusing on technical inefficiency. And again, there is a reason why we call it technical, because it's coming from the technology. There is no economics in there, right? Technology is technology. If you talk to an engineer, he or she will understand what a technology is. Technology of production of electricity, technology of production of anything. So this is again a concept that has no connection with economics, right? So again, when you talk about cost minimization, then economics comes in, because we are using a particular behavior, and the behavior is to minimize cost. That means you are using the inputs in a way that will minimize cost, and you are using the production function, right, in doing so. So then again, we go from non-economics to economics by estimating the production function, because a particular economic behavior is built in. But in doing so, we were assuming that there is no misallocation. Okay, that means, you know, allocation is exact. Let me just see whether I have a graph. No. Okay, so what do you mean by misallocation? That means the first order condition is not exactly satisfied. That means, well, when I was drawing the graph, I had this isoquant, and then I was looking at a point of tangency, right? And I said, well, this is the optimal point. And I was assuming that everybody is doing that. Nobody is making a mistake. But what happens if somebody is making a mistake, and again, instead of the optimal point, they are to the left or to the right of that? So what is happening? Because you are not using the optimal point, the cost of this point is going to be higher, because I have to draw in the line that goes through this point. And the line is about this solid line. And this solid line is indicating the cost, okay, and the dotted line is going to be indicating a cost which is going to be higher, because it's associated with, again, like even the price, again, you will see that, well, this has a higher cost. Okay, so then again, the way we say that, if you do not use the inputs optimally, you have suboptimal allocation, that will increase your cost. So that is going to be your cost of allocative inefficiency, right? So far we have not mentioned it, and there is a particular reason for doing that. Is complexity. As soon as we bring allocative inefficiency, things get mathematically complicated and also econometrically complicated. Okay, so the way we do is, we just said, well, if it is not equal, then you can make them equal. When something is not equal, you can always make them equal by doing some adjustment. So what is the adjustment? So I can say that, well, Fj over F1 equal to Wj over W1 times something else. So what is this? This can be bigger or smaller, right? So that means, well, what is this epsilon j? It can be positive or negative. So if it is positive, e to the power positive number is what? Bigger than 1. E to the power a negative number is less than 1. But they are all positive, right? So again, depending on the sign of epsilon j, it can be, you can move to a point to the left of the optimal point or to the right of the optimal point. So the misallocation can be captured by this term eta j. Okay, and then you go through the same type of thing. And if you do the product maximization, again, you do not equal the marginal product to the ratio of input prices normalized by output price, and again you can do the same thing. Okay. So now again, like the question is that this is kind of the model in the graph. Now, how can you express it mathematically, and then from there you can go to the parametrics. So this one is where we introduce allocative inefficiency. Since the production function is going to be expressed in terms of log, let's just think in terms of taking a derivative in terms of log, not in terms of the level. So when you do that, then this condition can be written like this. Okay, just simple algebra. Okay, and again, like this is again log of s of j. This is the factors here, minus log of again s of 1, and this is again if you take a log after so again this is log of wj over w1, this is beta plus log of xj over x1, and then plus epsilon j. Okay. So now what is happening is, if it is a Cobb-Douglas, then this is going to be equal to the constant beta j or alpha j, depending on how you specify it. So let's say this alpha j is the parameter here, and alpha 1 is the parameter for that. So this is really simple, and you estimate this along with the production function. Okay. So the complicating part is that so far this part was introduced 30 years ago, at least 30 years ago. But there is no program that will help you to estimate these things. So this is kind of a, because everybody is afraid of writing down codes that will do the estimation, not one equation but as a system. So this is what is happening. Okay. So again, to cut it short, says okay, this is how it's done, and then again we have the program. So if you go to the website of Hung and Wang, one of my co-author for the book, second book, not the first one, then you will be able to see that he has the SCADA codes in his website. So you can download the SCADA code free to estimate this type of model. So remember at the end, the very end, we were talking about we are interested in the cost, by how much the cost is increased because of misallocation or allocative inefficiency. So it's not only technical inefficiency, input-oriented ADA, but now we are adding one more thing, which is cost of allocative inefficiency. And what is that cost of allocative inefficiency? Now that would be the last point. So for this Cobb-Douglas case, the cost of allocative inefficiency is going to be, let me just see what I have. So this part. So this looks complicated, but once you estimate the parameters, this is a computation. Okay? It doesn't matter, I told you that you should not be afraid of the functional form. All you need to do is just plug in the estimates of those things, and then you will get. So this number is going to be giving you the percentage increase in cost because of misallocation. Okay. So in a nutshell, this is what is going on between estimating a production function and estimating a cost function. Okay. No new program is needed, and you get an additional thing if you want to include allocative inefficiency. Okay. Okay. So let me stop it.